to that. Okay, does that kind of make sense? All right, let's back on. So I now have also a mathematical way, because I think we can hopefully understand this from a visual perspective, what's going on here. But mathematically, it's a bit trickier, right? Because you look at this and you're like, where is any of this coming from? Let's draw it out. So this is our sort of situation here. I've got this vector, and I've got this vector, and I'm going to call, well, we're projecting B onto A, right? So this must be vector B, and this must be vector A here, right? And if I'm projecting, let's use a different color. I'm projecting onto it, right? So here's my torch. Ding! Let there be light. And what's our projection going to look like, remember? Well, remember, it's casting this light down, and the projection is literally another vector, right? P. Let's call it P, right? Very creative. Now, now here's the situation. I'm trying to find what this vector is. And we're really good at this now. But what is a vector actually defined by again? Remind me.
Magnitude and direction.
Yes. So a vector is equal to magnitude multiplied by direction. And the way we're going to find this is if we think about it. I want the magnitude of this, and I want the direction of this. And to find a direction, we talked a bit about this idea of a unit vector. A unit vector is a vector of a single length that goes in the same direction, right? So we say that this, we're looking for the unit vector, right? And the unit vector, well, which direction do we want this unit vector to be going in? This way, which is the same way as which one? A, that's right. So we want the unit vector of A. Do you remember how to find a unit vector, by the way? Check back in your notes if there's anything about a unit vector anyway.
Unit vector, like scaling it.
It is.
To do it one.
It is it's scaling it to a length of 1, right? And so the idea is, if you have a vector A, how can I scale it back to a length of 1? That's sort of the question. Check back in your notes if you can't remember. Yeah, you got it.
Is that actually?
That's actually it.
I just looked at the thing and
Yeah. Well, now you can start to see how this form is actually formed. Think about it from a conceptual point of view. You have a vector of length 5. How do you bring it back to length 1? Well, you take the vector and you divide it by 5, right? So the same idea here. We're speaking from a general perspective. I have a vector A. That's right. And I divide it by the length that it is. And what's our representation for length? It's magnitude of A, right? So far so good. The magnitude is going to be a bit trickier though. And the reason why it's trickier is I need to emphasize that when we look at sort of vectors, we need to make a clear distinction between vectors themselves and their magnitudes, because they're not the same. They're actually quite different. Magnitudes are lengths. Vectors are things with length and direction. So if I'm looking for just the magnitude, I have to deal purely with magnitude. I'm going to draw this, just this section here again, and hopefully it's clear what we can actually do to actually approach this. So let's say I have the magnitude B, and this is going to be magnitude P, and I will draw A all the way out anyway, okay? My question is this: can we find a way to represent P? Like, can we link P and B together? That's sort of my question. And the trick lies in, well, what kind of shape is this? It's a triangle. We could use Pythagoras. We can also use our angles. And I'll tell you why we'll use our angle in a moment. Because if I write this out, what angle relates these two together? What trig angle, or trig ratio relates these ones together? Cos, good, yeah. So cos theta equals to adjacent over hypotenuse, or P over B. I get that right? Yeah, cool. P over B. But, and this is the clue I'll give you, cos theta is actually special in terms of our vectors. And we learned about this last lesson, right? It's all sort of coming together. That's why we need things from previous lessons as well. And that's why we need to have a solid foundation of vectors. What's the significance of cos theta in terms of our vectors? If anyone remembers. on the previous exercise. So I'm jumping all around, but yeah, this is why I said it's so important to have a foundation on this. Cos theta is quite special.
Wouldn't it be the angle of elevation of like a vector to another?
What do you mean by that? Angle of elevation?
Because it's like kind of like where it like starts from the vector.
Yeah. Well, so if you notice actually, the theta, the angle is not just the angle between P and B, it's also the angle between A and B, right? And actually there's something to do with angles between vectors that we learned about last lesson. If we, yeah.
I'm just using the formula.
That's fine, yeah, that's fine.
Cos theta is equal to the dot product of A and B
Yep.
over the magnitude of A times B.
And this is why I'm emphasizing with mathematics, right? We have to have such a good foundation of things before. Otherwise, the things that we learn later on, we don't see the links and relationships between them. But what Caitlin's found is that, remember, the dot product, I may write on the side because it's kind of like a side note, the dot product of these two is equal, it has another definition, and it's this. What that means is that cos theta has another definition. What's the definition of cos theta? It's actually also equal to, as Caitlin rearranged for us, this. And again, same thing. Like if you only remember a formula, like this stuff is not going to make any sense. Like, but now we can see that, remember, if we remember this relationship, then we can bring it back to here. Because why is that important? We can replace now cos theta with this. And you might think to yourself, well, why is this helpful? What is this going to help us achieve? What it helps you achieve is the fact that now we can find an expression for the magnitude of p. Remember, that's the whole thing that we're trying to do, because we're trying to find the magnitude of this vector in terms of a and b. What do we need to do? There's one more step that we need to do. That's right. Exactly, and it simplifies out. All right, so just think about them like numbers. Like I'll multiply both sides by the magnitude of b. Okay, and actually what happens is they'll divide through. Because these are just numbers at the end of the day, you can do that, right? Magnitude is just a number, and this is what we get left with. And so let's come back to here and wrap it all up. What that means for me now is that I have an expression for the magnitude. It's this. So the length is just going to be, they're in red so you can see clearly, A dot B over A. And we're multiplying these two together. So what's going to happen on our denominator? Over here. A, yeah, absolute value of A squared. So A dot B over the absolute value of A all squared times that. And that's our projection of B onto A. That's our formula for that. How do you feel about that? Filthy. I think it's crazy. Just like you can derive this expression all by yourself using the knowledge that you have. So that's what I want to emphasize moving forward. Like when you see these concepts, it's so important they have a solid foundation of what we've learned so far.